Assalamu alaikum wa rahmatullahi wa barakatuh. Yes, gentlemen, like I mentioned earlier, if you remember on Wednesday, out of the 2 hours we were supposed to spend just total of 1 hour 40 minutes precisely. We were able to take only the first around 20 minutes. So we have 1 hour 20 minutes left, which I told you that I will surely make it up for you guys. Okay. So today I will make up for that class, and then remember we have 2 more weeks to make their own makeup lectures. That I will do subsequently, and I will inform you appropriately. Okay. Like I mentioned, if you don't attend the class now, you have to watch the video and understand. And if you have any questions, I will take it in the next class. Okay. In my previous class, I was able to finish with chapter 3, which is very long, although chapter 4 is also long, because now we'll start fluid kinematics. Okay, it has to do with fluid kinematics, which is chapter 4. Now we'll look at Bernoulli equation and pressure variation, and other stuff to do with flow classification. Okay, let me go to the right, the outcomes, the learning outcomes of this chart includes, distinguishing between steady, unsteady flow, uniform and non-uniform flows, and other types of flows as well. And then we look at this convective and local acceleration, and describe the steps to derive the Bernoulli equation and from Euler's equation, explain what is meant by rotation and vorticity of a fluid element, and describe flow separation. Okay? And the procedural knowledge include apply Euler's equation to predict pressure distributions in rotating flows and other stuff like that as included here. Okay, and the applications we have application variable area ducts, pressure and velocity distributions, a measurement of velocity with stagnation tube or a pitot-static. Fluid kinematics. Fluid kinematics, as the word implies, kinematics deals with describing the motion of fluids without necessarily considering the forces and moments that cause the motion. Okay, whenever something is in motion, whenever the body is in motion, then the force must be behind that motion. Okay, so in fluid kinematics, we are not necessarily considering the forces and moments that cause the motion. Okay, so we'll discuss the transformation of the conservation equations from the Lagrangian description of fluid flow to the Eulerian description of fluid flow. The Lagrangian description of fluid flow entails, as I mentioned here, following a fluid particle, individual fluid particle, and tracing its movement in space and time, okay, by finding its velocity at any instant of time and at any point in space for individual particles flowing in the flowing fluid. Okay, while the Eulerian description of fluid flow entails selecting a particular region in space called the control volume. If you remember, I explained the control volume. I think in chapter 2. Okay, so selecting a control volume and then trying to establish a field or develop a field or generate an equation of flow within a certain area by in space. Okay, so that any fluid passing that particular point in space should have that property. Okay, so here in the Eulerian description, we will introduce the concept of field. Okay, flow field, we'll look at velocity field, we'll look at acceleration field, and other stuff like that. We'll expatiate more as we move on. We'll explain, compare the two descriptive processes, okay, and so that it becomes clearer for you. Then flow patterns and flow visualization. Here, flow patterns, look at the flow patterns, the types of flow we have, and how it can be visualized. Yeah, some visualization to do flow patterns. While quantitative study of fluid dynamics requires advanced mathematics, much can be learned from flow visualization. Okay, that is using our eyes to look at how the flow particles are moving. Okay, that is the visual examination of flow field features. Flow visualization is useful not only in physical experiments but in numerical solutions as well. Okay, flow visualization is useful not only in physical experiments but in numerical solutions as well. That is, in the case of computational fluid dynamics, CFD. Maybe you have heard the word before, CFD, computational fluid dynamics. In this course, fluid mechanics, we will lay some of the most important foundations for anyone that wants to further on, his interest on the computational fluid dynamics area. The basic foundation will be laid in this course, okay, related to computational fluid dynamics, okay. In fact, the very first thing an engineer using CFD does after obtaining a numerical solution is to simulate some form of flow visualization so that he or she can see the whole picture rather than merely a list of numbers and quantitative data. So here we're still explaining the importance of flow visualization. It's very important even if you use the CFD to get numerical solution, because in the computational fluid dynamics you normally use numerical solution. You apply numerical methods to find the solution to the flow problems. Okay, so one needs to simulate some form of flow visualization. Okay, so as to understand the whole picture rather than just having some list of numbers and quantitative data. To make meaning to those data and numbers, you need to have flow visualization. Okay. Now, characterizing velocity. So, like I said, we'll start with velocity field. Okay, we'll start with velocity because this is fluid kinetics. The course is fluid mechanics. At the beginning, we looked at the properties of fluids in chapter 2. We analyzed all the most important properties of fluids. Okay, and then in chapter 3, we looked at fluid statics. We looked at all the parameters, all the processes that affect fluid at rest. Okay, so we look at many processes, okay, many processes in chapter 3. And then now in chapter 4, we look at now, what about fluid in motion? Okay, and fluid in motion, it means it possesses velocity. Okay, even at rest, if the velocity is uniformly, it's not changing over time, then it is considered to be a static equilibrium. Okay, but here in particular, because we're looking at fluid in motion, so definitely the first thing that will come to our mind is that the particle is in motion. By virtue of its motion, then definitely it possesses velocity. Okay. Okay. And by virtue of possessing velocity, then that velocity, depending on the way it is, it can be constant, it can be variable. Okay? If it is variable, then definitely you will have acceleration, which is the rate of change of velocity with time. Okay, so we will start first, which is with one of the most important parameters of fluid flow, which is the velocity. Okay, it's one of the most important parameters for fluid in motion. Okay, velocity. Some you may say discharge, but discharge is also a function of velocity. Discharge is Q equal AV, is the cross-sectional area which is constant times the velocity. So the velocity is one of the most important flow parameter. Okay, so we look at it and examine it in total. Okay, and then from there we will look at some different types of flows and explain them. Okay, so all we will be doing now will be more or less laying some rock solid foundation to this chapter. Okay, the chapter has a lot of sections that we will explore deeply. Okay, but we need to lay some good foundation, good understanding of velocity field, flow types, Lagrangian and Eulerian approaches. And then we move to the acceleration field, and then we move to the Reynolds transport theorem and other stuff like that. Okay, so characterizing velocity of a flowing fluid. This section introduces velocity and the velocity field. Then these ideas are used to introduce two alternative methods for describing motion. I've started explaining these two alternative methods for describing motion. The first one, Lagrangian approach, which describes the motion of matter, okay? That is individual fluid particles, individual particles of matter, okay? And we have the Eulerian approach. Lagrange is an Italian scientist. Euler is a Swiss scientist. Okay, so all these approaches were obtained from their names. Lagrange, you have the Lagrange theorem, Euler's theorem. So they all are scientists that have worked so much in these areas. Okay, so we have the Lagrangian approach, which, like I mentioned, traces the path followed by individual particles. Okay, you can imagine if the particle is big, let's say an aeroplane, a jet, rocket, yeah, then that is somehow doable and not so cumbersome. But imagine fluid particles, in a cross section, fluid particles, you can have billions of particles. So you can imagine how you will trace individual particles when considering fluid flow. So when considering fluid flow, it becomes, very cumbersome to really use the Lagrangian approach. Hence the Eulerian approach, which now describe the motion at locations in space and try to assign the values at fixed locations in space so that any particle passing through that location is going to have that given or defined property. Okay, so the Eulerian approach becomes more practical when it comes to fluid mechanics. But like I said, we are going to expatiate more on each of descriptions later below in the subsequent slides. Now, describing velocity. Okay, velocity is simply the speed, isn't it? The speed with which liquid flows. Okay, and when we say velocity, because it has the magnitude and direction. So velocity is a property of a fluid particle, which gives the speed and direction of travel of the particle at an instant in time. Okay, at an instant in time, meaning it is an instantaneous value. Okay, so it's the distance traveled per time. Okay, and the mathematical definition of velocity is dv/dr. In this case, we're looking at the position vector. If you look at this figure here, we have two particles A and B, or fluid particles. This one is the velocity vector moving vertically downward, okay, from a tank with orifice at the bottom. Okay, so this is the position vector RA. Okay, so the change of the position with respect to time gives the velocity of that particle. Okay, and B is another particle approaching, the exit. Okay, and the arrow here indicates it's the velocity vector. Okay, the velocity vector. So here, where VA is the velocity of particle A and RA is the position vector of particle A at time t. Now, velocity field. The description of the velocity of each fluid particle in a flow is called a velocity field. Okay, like I mentioned, the description of the velocity of each fluid particle in a flow, just like in this figure, when we have an equation describing the flow of the velocity of each fluid particle in this figure, then we call that the velocity field. In general, each fluid particle in a flow has a different velocity. Each fluid particle in a flow has a different velocity. The velocity of the fluid particle will be dictated by its position and time, okay, because it is moving. So at any given instance of time, so we'll have velocity depending on position and time as well. Okay, it depends, it's a function of position and time. So that's why we have the velocity vector equal to V S R ft. S is space, t is time. Okay, so it's a function of space and time. Okay, so for example, if particles A and B in this figure have different velocities, these particles A and B, they have different velocities. Thus, the velocity field describes how the velocity varies with position and also time. Okay, so if we have a velocity velocity field in the second figure B here. Velocity field is the description of the velocity at each spatial location. Okay, so look at some kind of will I say streamline, the path taken by the particles. If you have three particles, A, B, and C, okay, at A it will take this path, B it will go straight, A it will take this path. Okay, so the velocity field will describe the velocities of each of these three particles at any instant of time. Okay, and at any location. Okay, so this water draining out of a tank, so the velocity of particle A, the time derivative, okay, and the velocity field represent the velocity of each fluid particle throughout the region of flow. Okay, a velocity field can be described visually. This is visual description of the velocity field, showing the velocity vectors. Okay, showing the velocity vectors and the path taken by like hypothetical three particles A and B at the top of the water surface. Okay, or it can be described mathematically. Okay, it can be described visually or mathematically. Okay, the mathematical description definitely should have terms in, involving space and time. Okay, involving space and time. For example, a steady two-dimensional velocity field in a corner is given by, okay, v equal 2xi minus 2yj. Okay, so this is velocity field. Okay, it says steady. As we are going to define, we will define the types of flow. Steady means, the velocity, the flow parameters do not change with time. So time is fixed. Okay, time is not a variable. Time doesn't affect the flow velocity, meaning at any instant of time, the velocity is the same. Okay, the velocity is the same. It does not change. Okay, when you fix a position and examine the velocity passing through that position, the velocity doesn't change. So that's why in this flow, in this velocity field, you have 2x minus 2y, 2xi minus 2yj. I and j are the unit vectors directed along the x and y coordinate axis. Okay, the unit vectors. This you must have done in statics. Okay, they are unit vectors just indicating the direction. Unit vectors are simply giving direction to forces or to vectors. Okay, they have unit of 1. Okay, they are dimensionless, their value is 1, so they just give the direction. I for x-axis, j for y-axis, and k for z-axis. Okay, so you have 2x minus 2y, 2xi minus 2yj. You see, in this velocity field, you don't have any term in t because they said the flow is steady. If it is steady, it means time does not affect the velocity, meaning the flow, when you fix a space at any but when you look at the flow at a given point, the flow doesn't change. Let's say you take this height. Okay, the flow velocities of A, B, and C do not change with time, irrespective of time. When you watch for 2 minutes, 3 minutes, the flow velocity remains the same. Okay, that is what is meant by a steady flow. And two-dimensional, because you have the velocity varying in two axes, x and y. Okay, later we are going to explain, one-dimensional flow, two-dimensional flow, and three-dimensional flow. Okay, that is when the velocity varies, is it along one axis, two axes, or three axes. Okay, so this we will examine later, but this is just an example of a velocity field, the mathematical representation of a velocity field. Okay, this is mathematical, and this is visual. This figure B. Okay, it is the visual representation of velocity field. When a velocity field is given by an equation, a plot can help one visualize the flow. This we have seen. Okay, the code of a field can be generalized. A field is a mathematical or visual description of a variable as a function of position and time. Okay, we have seen in the velocity field we have x and y, which is function of position. We don't have any term in t because it is a steady flow. So that is the velocity field does not contain any term in t because it is a steady flow. Now, this is even the velocity field, you know, that we have worked with in the previous example. Then we can visualize it, you know, the field using the velocity vectors and the streamline pattern. Okay, with this velocity field, we can plot it out on x and y axis, okay, by choosing some values of x and y and then plotting the points. For instance, you can take x and y to be 1, 1, and then substitute the value here. When you substitute the value, you can plot it 1, 1, okay? When you plot it, you will have this velocity vector here, okay? This one, velocity vector with the direction, because when you plot it, you will have v to be equal to 2i minus 2si minus 2. There'll be no x because x is equal to 1, so it'll just be 2i minus 2j. Simple. 2i minus 2j. And 2i minus 2j, this you can plot visually, okay, using your knowledge. This you can plot using your knowledge of vectors, okay. 2i, it means is along the positive x-axis, minus 2j is along the negative y-axis, and the magnitude is both. Here you can find the direction, okay, the direction, and the magnitudes are the same, so the direction theta will be 45 because fx is equal to fy, okay, so theta will be 45, so it's going to be something like this, okay, and that is why we have this particular value here. This is just for x equal 1, 1, so you can just select some points, some combinations of x and y to plot this velocity field, and when you do that, you obtain figure A, okay. You can see at this point, this is one of the points, this is another point, this is another point, and this is the velocity field, and this is the direction, the velocity vector. Remember, velocity is a vector, so it has magnitude and direction and sense, okay. The sense is represented by the arrow, and the direction is given by the angle of inclination to any of the axes, okay. Now, in the second part, the second figure, we have B. This is the visual description, a plot of the velocity vector, which is this one, by selecting any combination of x and y and plugging them here and plotting the resultant equation using our knowledge of vectors by calculating the angle in each case. Okay. Streamlines. Streamlines are always tangent to the velocity vector. So from this plot, we can sketch this streamline, okay? We can sketch this streamline. Streamlines are always tangent to velocity vector, okay? Always tangent to the velocity vector, okay? You can see this is touching here is tangential at this point, tangential at this point, okay? And we can also sketch the second one, okay? You can see this is tangential here, tangential at this point, tangential at this point, okay? And we can also sketch another one, the third one, okay, depending on the points that we have. So that will now take us to this one, okay? So streamlines are lines that are always tangential to the velocity vector, always tangential. So the velocity vector is all tangent to the streamline. It's always tangent to the streamline, always tangent to the streamline, okay? It gives path followed by individual. It means you will have flow in this. Particles are going to move. It gives the direction of flow. Give the direction of flow. These are the velocity. They have the direction, the sense of flow following these specific streamlines. They are following streamlines. We are going to explain more on, okay? Just so you know, this is very important. When we plot the velocity field, okay, the velocity vectors. From there, we can sketch our streamlines, and streamlines are always tangential to the velocity vectors, which represent the direction of fluid flow. Okay. So other examples here, you can have, this is velocity field. You can have pressure field. Okay, because it doesn't mean you must have a vector. A parameter must be vector. Okay, you can have pressure field, which will describe the distribution of pressure at various points in space and time. Okay, and you can have temperature field, which describe the distribution of temperature at various points in space and time. This we demonstrated using the velocity field because, like I said, velocity is one of the most important parameter affecting fluid flow. Okay, if we look at pressure, pressure is changed by velocity. Okay, one way or another. If we look at temperature, although temperature affects the velocity of flow, because when it increases, you know, the viscosity reduces, and then the velocity could increase depending on other factors. But like I said, we'll be using the velocity as an example. But you have other fields. We can have pressure field, temperature field. Like here we are looking at the most important one and examining the velocity field, and later we'll look at the acceleration field as well. A field can be scalar valued, e.g. temperature field, pressure field, or vector valued, e.g. velocity field or acceleration field. Now, representing velocity using components. We have seen even in the velocity field, we have x and y components. So this is a general representation of velocity. We have u, which is a function of x, y, z, and t. X, y, z because the velocity varies in 3 directions. Okay, and you have v, you have w. Okay, so this is I, j, k, the unit vectors directed along the 3 coordinate axes. Okay? So another way to represent a velocity is to use normal, tangential, and tangential components. Okay, and in this approach, we have unit vectors that are attached to the particle and move with the particle. So when you have a particle moving from point 1 to point 2, in this case, okay, so describing the motion of a particle using normal and tangential components. The particle has traversed a distance s. Okay, you have the unit vector directed normal to the flow path. Okay, and you have normal unit vector that is tangential to the flow path. Okay, so the tangential unit vector is ut and is tangent to the flow path of the particle, and the normal unit vector is un, and which is normal. Normal meaning perpendicular. Normal, you know, when we say normal, we mean perpendicular at 90 degrees to the flow path and directed inward toward the center of the curvature, the center of curvature, because this is curve. Okay, so it's directed toward the center of curvature. So here, position coordinate s, okay, measures distance traveled along the path and the velocity of a fluid particle as a function of the tangential component. V equal V, which is a function of f, the unit vector in the tangential, okay, along the tangential, where V is the speed of the particle. And okay, so this is another presentation. Position and time times a unit along, you know, the tangential unit. We can use this first representation, or which is the second representation, tangential unit. Now, here we have started going deep into describing flow of particles. Okay, if you look at this, we are taking a particle of fluid moving from point 1 to point, okay, and tracing its path. Okay, now we'll look at flow description, and we'll start with path line. Path lines, okay, as the name implies, path line. Path line is the path of a fluid particle as it moves through a field. The path traversed, okay, by a particle, it moves a flow field like a trajectory. the trajectories that individual fluid particles follow. Okay, this can be thought of as recording the path of a fluid element in flow over a certain period. Okay? And path lines are the easiest of the flow patterns to understand. Just imagine, let's say you want to move from here to town, okay, from the university. You move your car to the gate, and then you take left, to the junction. You move right, straight down, till downtown. So that is the path taken by you if you consider yourself as a fluid particle. Okay. A path line is a Lagrangian concept in that we simply follow the path of an individual fluid particle as it moves around the flow field. Remember, I explained the Lagrangian concept in which we follow individual particles as each of these particles at different points in time. Okay, this is T naught, the beginning of the time. Okay, T1, T2, T3, T4. Okay, and tracing their path. Thus, a path line is the same as the fluid particle's position vector. So it's simply the fluid particle's position vector, which is a function of time. X particle function of time and Y, Z all function of time, traced out over some time interval. Okay. Path lines can also be calculated numerically for a known velocity field. Okay. If the velocity field is known, then we can calculate the path line numerically. Specifically, the location of the tracer particle is integrated over time from some starting location, which is x. X is a position vector. That's why it has the vector notation. Okay, from starting point at a starting time to a later time. So how do we do that? The tracer particle at location at t, which is x bar, will be equal to the beginning, the position vector at the beginning, plus the integral of the velocity vector dt, t from the starting time to the time of interest. Okay, so what is most important here, if we know the beginning of the particle, the starting point, and then we know the velocity field, then we can trace out the path line, okay, using this equation. When this equation is calculated for t between t start and t end, okay, a plot of xt, okay, a plot of xt is the path line. Is the path line of the fluid particle during that time interval, as illustrated below. Okay, so if you have this, okay, this is the starting point. Okay, this is the initial point. Okay, this is the path taken by the fluid particle at some intermediate time, and then it moves. This is the end time. T equal t end. The path line is formed by following the actual path of a fluid particle, just like tracing. We are tracing out the path traversed by the fluid particle. Okay, and simply plotting, xt versus time will give us the path traversed by the fluid particle. Okay, to give us the time, the path traversed by the fluid particle. Don't forget, all these are vectors. Okay, this is a vector, and this will result into a vector. So when we plot the vector, the space field, okay, with respect to time, it will give us the path taken by that particle. If the velocity field is steady, individual fluid particles follow streamlines. Okay, meaning if the velocity field does not change with time, okay, at a given point in space, individual fluid particles follow streamlines. Meaning they follow a clearly defined patterns. Okay, I told you we just plotted a streamline, which is a line that is at any point tangential to the velocity vector. Remember, we plotted the velocity vector and then we joined the points, okay, by a streamline. Okay, a streamline is simply a line that is at any point tangential to the velocity vector and gives the direction of flow of the fluid. Okay, so if the velocity field is steady, individual fluid particles will follow streamlines. As for steady flow, path lines are identical to streamlines. Okay, for steady flow, path lines are identical to streamlines, which is very important. Okay, for steady flow, path lines are identical to streamlines. Why? Because they do not change with time. Okay, streamlines are like time snapshot. At an instant of time, what is the streamline? What is the velocity vector like? Okay, what is the path line at an instant of time? You can see that path line is time averaged. Okay, it's over given interval of time. That's why you have t start and t end. Okay, t start and t end. So it's like time averaging. We're integrating the time over some time interval. But for streamline, we are fixing the time, okay, and then observing the flow. What is the flow pattern at a given point in time? So this is very, very important. But when we have steady flow, like in this case, yeah, for steady flow, the path line and streamlines are the same. We mentioned that this velocity field is for a steady flow because it doesn't have any term in t. Okay, so it means that path line and streamlines are the same here. Many individual particles will follow these streamlines. Okay, and each one of the streamlines here are representing different paths for different particles. Okay, different path for different particles, and at a given point in time. Okay, let's say at time equal 2 minutes. Okay, then this is the streamline, and that is why you cannot have one particle jumping from one streamline to another. It doesn't cross. Particles do not just cross over from one streamline to another because you cannot have more than one particle in two different places. It's like you, like myself, I'm now in my office. I cannot be the same person. I cannot be present, let's say, in Hyperpanda, in Makanmore. I have to be present in only one place, one location in space. So I was explaining for steady flow, path lines are identical to streamlines. Okay, path lines are identical to streamlines. Okay, and that is because the streamline for steady flow indicates the path taken by individual particles. Okay, in that flow field. Streamlines. I've already started explaining what streamlines are, but this is where we will, officially discuss each of the aspects. That are pertaining to streamlines. Streamline is defined as a line that is tangent everywhere to the local velocity vector. This we have demonstrated before, where we plotted the velocity field and then joined, the velocity vectors by streamline. Okay, it's a line that is tangent everywhere to the local velocity vector. Okay, if you look at this figure, okay, flow is flowing out. Okay, if you have three particles A, B, C, okay, A will follow this path, will go up B, C. So at any point, okay, you have the velocity vector. When you have the velocity field and try to plot it, the streamline is tangential at any point. Okay, the velocity vector is tangential at any point to the velocity vector. It is a line drawn through the flow field such that the local velocity is always tangent to the streamline at every point along the line at that instant. It's very important at that instant because I mentioned which is time average, which is over a given time interval. Okay. Streamlines do not be because based on the velocity vector, the flow field can change in the next time. The next instant of time. So streamline are given for a specific time, okay? And there is no flow normals to streamlines. No flow normal to streamlines. I mentioned this. No flow normal to streamlines, okay? Because this is the velocity vector, okay? Normal to the velocity vector, and the velocity vector is always tangent to the streamline. So there is no flow normal to the velocity vector. The flow has to be along the velocity vector, not normal. It will not have component normal to it. Normal to it, the velocity vector will have 0 component. So there is no flow normal to a streamline. This is another example when you have streamline. Okay, these are the example of the velocity vectors. Okay, these are the velocity vectors. So normal to them, you don't have flow because the velocity component normal will be 0. Okay, it's just like you having force. Let me say, you have force directed here. What's the component of, let's say, force of 10 Newton directed along the y-axis, the x-axis? What is Fx? The component of this force along the x-axis, it is 0 because it is normal. Okay. At the location where the dividing line intersects the body, you look at this dividing streamline. This is called dividing streamline. It intersects this body. This is airfoil or aerofoil. Aerofoil can be like a wind of an airplane. So it is called airfoil. So this is dividing streamline, and it is intersecting the body at the point where it just touched almost perpendicular to the body. The velocity will be 0 with respect to the body. This is called the stagnation point. Okay? Stagnation point. We will use this point in the Peter tube when evaluating the measurement of velocity. Okay, so at this point, at the stagnation point, that is the point where the dividing streamline touches or hit the body. Okay, the velocity at that point of that particle is 0. You can see other particles are moving away. Okay, are moving away. So the velocities of these ones are not 0. But for this one, at this point, the velocity is 0. Okay. Streamlines cannot be directly observed experimentally, except in steady flow fields. Okay, they can only be observed experimentally in steady flow fields, because in steady flow fields, you have the velocity field not being a function of time at all. Okay, so meaning the flow field remains constant, it remains the same. Remember I told you streamlines are, instantaneous at any instant of time. Okay, are instantaneous values. So if time is not a factor, that is when you can observe it experimentally, in which they are coincident with path lines and streak lines. I explain what path lines are. I will explain streak lines in the slides to come. Okay. So because you can observe them because they are coincident with path lines and streak lines. Okay, and path lines can be observed experimentally using tracer studies. Okay, and some cameras, to take some snapshot to look at how the fluid is flowing. So this is another airfoil. You can see the streamlines being compressed here over the airfoil, and they're moving out, spacing out because of shear, because the airfoil will introduce shear. Okay, it will introduce shear stress. Okay, shear stress will be introduced here, and there will be drag. Okay, thus hitting. Imagine this streamline hitting this. Okay, it will exert drag. Okay, drag force. Okay, you remember we mentioned all the forces acting for fluids. One of them is drag force, which is the force exerted in the direction of flow of a fluid. Okay, in the direction of fluid flow, you have drag force. So here, if you have drag force, perpendicular to the drag force, you have lift force. Okay, this is drag force. And perpendicular to the drag force, you have lift force. All these are forces acting on bodies in fluids. Okay, and remember we talked about the buoyant force. Okay, we talked about the pressure force. Okay, so all this. Okay, so this drag force, depending on the geometry, you can see this aerofoil may exert little drag because only this will hit it, assuming the body is shaped this way. So many streamline will become dividing streamline, okay, and thereby exerting drag. Okay, and that is why airplane is shaped such that it is something like this to allow smooth flow of air around the wings. Okay, and even our cars now are so designed that they will allow smooth flow of air around them. Okay, over them, below them, to reduce the drag force exerted on these vehicles, because the drag force can have tremendous impact on the stability, most especially when we're talking about aeroplane. Okay, and in case of automobile, our cars, okay, it can have significant impact on the speed of the car. Mathematically, however, a simple expression for a streamline based on its definition. Remember, we explained how the mathematical expression of path line. For streamline, here, if we consider an infinitesimal arc length, okay, if we have a streamline, okay, we consider an arc length here, okay, a small arc length, okay, dr is the position vector, which is given by ijk, dx, dy, dk along a streamline. Dr must be parallel to the local velocity vector, okay, dr must be parallel to the local velocity vector, okay, and this is the local velocity vector. And the equation for streamline, if you look at this is point xy, okay, so this is dx, dy, that's after some time, okay, it has moved to this point, and this is the local velocity vector. Because it is parallel, it has to be along the local velocity vector. It's tangential. So we'll produce the velocity vector, okay, so this is u and v, okay. Here, for two-dimensional flow in the xy plane, the arc length along a streamline is everywhere tangent to the local velocity vector. Okay, so here we're considering two-dimensional flow, and this new angles, dr is equal dr divided by v is equal to dx divided by u, okay, which is equal to dy divided by v, which is equal to dz divided by w, okay. And then from here, if we take any two of these equations, dy dx will give us u v over u, okay, which is along a streamline. Remember, u is a function of x, y, z, and t, okay. Also, v is a function of x, y, z, and t. Also, u is a function of x, y, z, and t. So if these functions will be defined, the equation of the streamline will become evident, okay. dy dx is equal to u v over u, okay. On streamlines, an arbitrary constant of integration, because there we say dy dx, okay. So we need to, if we have the functions of v and u, we need to integrate to find y, okay, as a function of x, y, and t. So when we integrate, we have arbitrary constant of integration, which appears when solving the streamline equation, okay. And then we can plot each chosen value of the constant of integration represents a different streamline, okay. So we can have, let's say, y equal mx plus c, where c is the constant. So each chosen value of c will give us a different equation, isn't it? So we'll have family of curves that satisfy the same equation, which represent the streamlines of the flow field, okay. So you can see all these are the streamlines and these are the velocity vectors. Okay. When you have any given value of c of the constant of integration, you'll have a different streamline. Okay? And streamlines are useful as indicators of the instantaneous direction of fluid motion throughout the flow field. This I mentioned ab initio. And stream tube. Okay, stream tube consists of a bundle of streamlines. Okay, much like a communications cable consists of a bundle of fiber optic cables. Okay, when you have many streamlines collected, okay, so they form what is called stream tube. Okay, and since streamlines are everywhere parallel to the local velocity, they are everywhere parallel to the local velocity, fluid cannot cross a streamline by definition. No fluid can cross a streamline because there will be no flow across a streamline, because there will be no flow across the velocity vector. Okay, this I explained also. By extension, fluid within a stream tube must remain there and cannot cross the boundary of the stream tube. Okay? Fluid, let's say, contained within this stream tube must remain there and cannot cross the boundary because there is no flow across the boundary of any streamline. And by definition, also, different streamlines at the same instant in a flow do not intersect. Okay? Do not intersect because a fluid particle cannot have two different velocities at the same point. You cannot have streamline this way and then another one crossing. Okay? They do not intersect because at the same instant of time, it cannot have different velocities. Okay? Not have different velocities because this one will have velocity, the tangential velocity is this one, the tangential velocity is this one. Okay, so for that, streamlines cannot cross over. Okay, and again, you see, this is a converging tube, okay, in which the streamlines are converging, okay, which means the flow, the velocity is decreasing towards the exit, okay, towards this. No, the velocity will increase because the area has decreased, okay, so the velocity will definitely decrease, okay, and for this one is diverging, so the area is increasing, so the velocity, so the diverging area is decreasing because of the increase in the area. Okay, remember, though, we will show that the discharge is equal to the area times the velocity. Okay, so to ensure the same rate of flow, okay, the area and the velocity will keep on changing. So you can see here the velocity is reducing, is increasing, while this is increasing towards the exit, and this is decreasing, okay, towards the exit because of the increase in the area. But the streamlines are all parallel. Okay, they are all parallel. Now, the next one is called streaklines. So we discussed about pathlines, and then we talked about streamlines and non-path streaklines, streamline and then non-streaklines. If you remember, we said pathlines are the actual path taken by the fluid particles, and the streakline is the line generated by a tracer fluid, such as a dye, continuously injected into a flow field at a starting point. So here you're talking about many particles. So the calculation of the mathematical expression of the streakline is similar to that of the path line. This is the position vector for the injection point, okay? And then once you know the velocity field, you integrate it with respect to time of injection and the present time, okay? Streakline concentrates on fluid particles that have gone through a fixed station or point, okay? So in the path line, we're talking about one particle, okay? In the streakline, we have combination of particles traversing the same path line over time. For instance, here, the streakline is formed by continuous introduction of dye or smoke from a point in the flow. This is that is introduced here. You have flow. This is object. Okay, so this is the path taken by the fluid particles. Okay, this is fluid particle number 1, 2, 3, 4. So they are all following the same path line. Okay, the same path line, and that constitutes streak line. That path line that is followed by numerous particles injected. Okay, so it represents the locus. Locus is simply an equation describing the path followed, or satisfied by so many points in space. Okay, in this case, it is the path followed by the individual fluid particles. Okay, it represents the locus of fluid particles that have passed sequentially through a prescribed point in the flow. Okay, and this is the point from here to here. Okay, so all the particles injected are following this path line. So it constitutes a streak line. Okay, streak lines are the most common flow pattern generated in a physical experiment. Okay, in a physical experiment, normally we generate a streak line because normally we inject fluid particles. Okay, not just one particle. Okay, we inject them and then we trace, the path traversed by these particles. And this figure shows a tracer being injected into a free stream flow containing an object, such as a wing. Okay. The cycles represent individual injected tracer fluid particles released at a uniform time interval. Okay, at a uniform time interval. You can see the particles here are accelerated. Okay, the difference between the particles is higher because they have higher velocity here. Okay, as the flow is going over the object, they get acceleration, they get accelerated. Okay, and why do they get accelerated? Because Q equal AV. The cross-sectional area has reduced, okay, because of the presence of this object, so the velocity has to increase if this has reduced to maintain the same flow. So that is why the space between them is higher along the object than at the injection point to where the object begins. Okay. As the particles are forced out of the way by the object, they accelerate. Okay, just mentioned around the shoulder of the object, as indicated by the increased distance between individual tracer particles in that region. Streak line is formed by connecting all the cycles into a smooth curve. Okay. So now I'm comparing streamlines, streak lines, and path lines. When flow is steady, path line, streak line, and streamline look the same so long as they all pass through the same point. Okay, this I mentioned. Okay, if flow is steady, and you can also see that streak line is a function of time interval. Okay, it's a function of time interval. It's time to inject and time to present at the point of observation, while line is instantaneous. Okay, streak lines and path line are all functions of time interval. They are time integrated values. But for steady flow, okay, when the flow doesn't vary with time, then all of them represent the same thing. Okay, streak lines will represent path line and will represent streamlines. Okay, that's the streak line, which can also be revealed by experimental means to show what the streamlines what the streamline looks like. Similarly, a particle in the flow will follow a line traced out by a streak line. So this is an example in which you have a steady flow, streak lines produced by colored fluid introduced upstream. Since the flow is steady, these streak lines are the same as streamlines and path lines. Okay? So this is like an example of a velocity field in which it is unsteady. Okay, it is unsteady flow because you have t. Okay, the velocity is a function of t, hence it is not steady flow. Okay, in this case, you have the streamlines, path lines, and streak lines oscillating. Okay, for the velocity field, streak lines and path lines are wavy because of their integrated time history. Okay, but the streamlines are not wavy because they represent an instantaneous snapshot of the velocity field. And here they are like sinusoidal because you have sine omega t. Okay, that's why the streak lines and path lines are sinusoidal, and they are different. You can see for unsteady flow. And these are the streamlines. The streamlines are not sinusoidal because they represent like a snapshot of the velocity field at a given time. That's why like the streamline here is at t equal to, while the path line and the streak lines are from 0 to 2 seconds. That is a time interval, while streamlines are at a given point in time. Okay, a specific point in time. Okay, what is the flow field like? Okay, so this represents the flow field, and these are the path lines, and these are the streak lines. Okay. Now let's take about 3 minutes break, and then come back to continue with the Lagrangian and Eulerian descriptions of fluid flow. Shabab, let's continue. Where we stop. Now, Lagrangian and Eulerian descriptions. I've already started explaining these concepts and what they entail. Okay? In solid mechanics, it's straightforward to describe the motion of a particle or a rigid body. This we did in statics and what have you. But then when you have fluid flowing, okay, it becomes more complicated. Okay, and it is not practical to track the motion of individual fluid particles because there are billions in number. Okay, the flow, parameters change with time and with space. So tracking each one becomes, a Herculean task that is almost not achievable. Thus, researchers invented a second way to describe motion of part fluids. The first way to describe the motion is called the Lagrangian approach, which involves selecting a body and then describing the motion of this body. And the second one involves selecting a region in space, okay, and then describing the motion that is occurring at point in space. Okay, you select a region in space, and then you now describe the motion that is occurring at points in space. Okay, which is the Eulerian approach. In addition, the Eulerian approach allows properties to be evaluated at spatial locations as a function of time, because the Eulerian approach uses fields, okay, like the velocity field, okay, so understand the velocity at any instant of time at any given location for any fluid particle that is passing that particular location. You can imagine this method of describing motion is much more difficult for fluids than for billiard balls. Okay, when you have, let's say, the snooker ball, there's billiard balls, you can trace each one, the movement, the velocity, and with a small number of objects, such as billiard balls on a pool level, individual objects can be tracked. First of all, we cannot easily define and identify fluid particles as they move around. Okay. As for the Lagrangian approach, we need to keep track of each of these particles, their position vector, as well as the velocity vector, okay, as they move around. And this becomes a Herculean task. And secondly, a fluid is a continuum, okay, from a macroscopic point of view, okay. So continuum, yeah, it is so much connected together that the properties may not be isolated. I mean, properties of one fluid particle is so much impacted upon by other fluid particles. Okay, so it doesn't work in isolation. The particles do not move in isolation or completely independent of us. Okay, so interactions between fluid particles are not as easy to describe as are interactions between distinct objects like billiard balls or air hockey pucks. Okay. Furthermore, the fluid particles continually deform as they move in the flow. Okay, because once you have shear stress, I mean, they continually deform under the action of shear stress. Okay, so that makes it more difficult to track, I mean, the movement of the individual fluid particles. Okay, so this. So, so describing motion is much more difficult for fluids than for billiard balls, and first of all, we cannot easily define and identify fluid particles as they move around. Again, secondly, we mentioned fluid is a continuum, so there is interaction between them, okay? And fluid particles differ continuously. Instead of tracking individual Instead of tracking individual fluid particles, which is the Lagrangian approach, we define field variables, which is the Eulerian approach. And these field variables are functions of space and time within the controlled volume, like the velocity field, temperature field, or pressure field. The field variable at a particular location at a particular time is the value of the variable for which ever fluid particle happens to occupy that location at that time. Okay, for instance, you can have the pressure variable. Okay, you can have the velocity field, the acceleration field. Okay, so these variables, these variables, they give the particular value of whatever particle that happens to occupy that location at that point in time. Okay, unlike the Lagrangian approach in which it tracks the movement of a given particle only. So this like defines a region in space that whatever particle is occupying that region in space, then the particle properties is given by the field variables. Okay, so it makes it simple to analyze, but still coming up with the field variables may be more tasking than coming up with the tracking of particles. Okay. Now this figure shows small particles released from rest and falling under the action of gravity. They are released from rest from this container and falling under the action of gravity. Equations on the left side of the image show how motion is described using a Lagrangian approach, and the equations to the right show Eulerian approach. Okay, so for this particle, for example, for this particle, the equations are, V equal gt, because they are released from rest, so initial velocity u equals 0. Remember, in dynamics, v equal u plus gt, and they are under gravity, so acceleration is g. Okay, so u is 0. That's why v is equal to just gt, and s, that is the distance traveled from rest to this point, is half gt squared. Remember, s is equal to ut from dynamics plus half gt squared. So u is 0, so 0 times the time, we have s equal half gt. Okay, this gives the velocity and the distance traveled by this particle. Okay, now use Eulerian description. Okay, at any location in space, the speed of a particle is given by v equals square root of 2gz. Z is the vertical location. Of course, this is also obtained from the equation of motion. V equal u squared plus 2gz. Z is the distance. Okay, u, because initial is at rest, so the initial velocity is 0. So v here is now the square root of 2gz. We put in modulus because when you go down it's negative, so we're taking the modulus, the positive, the absolute value. Okay, and here you can see that v does not have any term in t. Okay, meaning it is steady flow. Yeah, because it is flow under gravity. It is flow under gravity. The velocity does not change. Okay, because of the acceleration due to gravity acting. Okay, and this is irrespective of the mass of the object. Okay, irrespective of the mass of the object, provided you don't have air resistance. If you are to this experiment that Galileo performed, okay, to understand or to prove that heavy object and lighter objects will fall at the same time to the ground if there is no air resistance. Okay, you need 100 kg and 1 gram. Imagine 100 kg and 1 gram. They will all fall to the ground at the same time when released from the same height above the ground level. Okay, so the movement is steady. That's why the velocity is the same. It doesn't change, and the acceleration is the same also. Acceleration due to gravity. Okay, which is g. Okay, which is the acceleration of all objects falling. Okay, so that's why it is not a function of time. Now, Comparing the two methods or approaches, the Lagrangian and the Eulerian descriptions, you know, the basic idea here: you observe or describe motion of matter, fixed identity. In the Eulerian approach, you describe the motion of matter at spatial locations. Okay, the solid mechanics used in dynamics, the Lagrangian approach, here also used in elasticity. Okay, and can be used to model the flow of materials. But for fluid mechanics, all mathematical equations in fluid mechanics are written using the Eulerian approach. Okay, we can also derive some stuff using the Lagrangian approach. Okay, equations may be often derived from a Lagrangian viewpoint, because we look at a particle, derive the equation, and then integrate it, okay, over to now generate the Eulerian counterpart. And here are the independent variables. You have the initial position and time, and here select a spatial location and time. And mathematically here, this one is simpler, the Lagrangian approach, and this one is more complex. For example, we usually have partial derivatives and non-linear terms that appear because we are not dealing with only one particle. Okay, the field concept here, field concept is not used at all, and the Eulerian approach, we use the field concepts. Okay, so when fields are used, the mathematics often includes divergence, gradient, and curl. Okay, all these are things you learn probably in vector calculus. Okay, divergence, gradient, and curl of a vector. Okay, they form part of vector calculus. I don't know if it's math 202 or 301. Okay, probably 202 maybe, or maybe 202. Yeah, divergence, gradient, and curl of a vector. It is under they fall under calculus. So, and the types of systems used for the Lagrangian, you have the closed system, particles, rigid bodies, and system of particles. And here we use the control volumes for the Eulerian approach. Okay. Now, my time is up. Just 1 minute to the time, because we'll spend 80 minutes now. And then, like I informed you earlier, we have other lectures to make up, and I will inform you in due course. Okay. Then the next topic we are going to look at will be the classification of flow. Okay, yeah, we'll look at uniform, non-uniform flow, steady, unsteady flow, and all different other types of flows, their characterizations, explanations, and all that. Thank you so much. And if you have any questions, you can ask.